So it's my pleasure to introduce Professor Aydogan Ozcan from UCLA for the next invited talk. Aydogan is a pioneer in many areas of computational imaging. I remember reading a lot of his papers when I was in graduate school. And one of the things that was interesting when I joined UCLA is I'd always gotten used to reading the spelling of his name. So Ozcan Lab or Ozcan Lab. And so when I joined UCLA, I realized that actually I was pronouncing it wrong for many years, that the name is actually pronounced somewhat close to Aydogan Ozcan, is a little bit closer to that pronunciation. Aydogan has done a lot of work in biosensing, nanophotonics, point-of-care diagnostics. When cell phone microscopy started taking off, Aydogan was one of the pioneers in his lab. Recently, a few years ago, he published a paper with his group in Science in about, I think, 2018, if I recall, that opened up a new area of machine learning effectively at the speed of light. And he may touch on that in his talk. Aydogan is the Chancellor's Professor at UCLA, and he's also a Howard Hughes Medical Institute, HHMI Professor as well. He's also won the Guggenheim Fellowship, PKs, TR35, and many prestigious awards. So with that, let me turn it over to Aydogan for this invited talk.
Thanks for having me. Let me time myself. So it's a great pleasure to be here. Thanks again for this warm introduction and for having me here. Today I'll talk to you about diffractive optical computing and how we're engineering materials at the scale of wavelength to compute as light is diffracting. So there are three areas that diffractive optical networks, diffractive computers, diffractive deep neural nets, all of these will be interchangeably used in my talk that I believe will be impactful for the field. First, all optical statistical inference. So you can use and build these diffractive elements, very thin elements for speed of light inference. You can build computational cameras of all kinds. For microscopy, for sensing, for defense-related applications. And you can also think of this as a black box for inverse optical design. You can create various interesting input-output relationships with diffractive networks. So a diffractive network is composed of transmissive and or reflective elements, where each one of those lambda over to half a wavelength element, which we call them diffractive neurons, of a plane is a trainable parameter. Its phase and or amplitude coefficient is trainable. You set a certain task for it to solve, and the training is done using standard deep learning tools, using a computer. Once it converges, then you have the diffractive elements to be fabricated, to be printed, to be using lithography created and assembled to form a system. So one of the major advantages of this kind of a scheme is that it doesn't consume power when it's computing, except the illumination light. It computes through passive material diffraction. It finishes its computation at the speed of light propagation through thin elements. If you're looking at the visible wavelengths, this is maybe 0.1 millimeter thick in terms of its total thickness. So you're talking about a very compact material that calculates and finishes its computation with low latency. It's also scalable, obviously. You can fabricate larger areas. These are diffractive networks where every single secondary wave, a spherical wave based on the Huygens principle, is creating a soup of coherent waves or partially coherent waves that are being modulated deeper into the network. There is depth feature, as I'll highlight in the next few slides, where distributing the same number of trainable diffractive neurons, diffractive elements, in a deeper architecture benefits the learning and benefits the overall generalization, whatever task it is that you want to implement with these systems. I'll start with some classification tasks to warm up, but most of my time hopefully will be spent talking about computational imaging applications of diffractive systems trained with deep learning. Most of what I'll show today if there is an experimental demonstration, that's going to be done in terahertz waves. That's why these black-looking 3D printed polymer structures, these are diffractive networks that are transparent in terahertz waves, and every feature here is half a wavelength of a terahertz beam being approximately, let's say, 0.7, 0.8 millimeters. The good thing about a diffractive network is it can be shrinked. Everything scales with the wavelength of light. The design doesn't change. Unlike metamaterial-based systems, you can take a dielectric diffractive network and scale it. So this one, for example, is a classifier for MNIST, which means if you show, after its training and if you fabricate it, if you show a new test object number 5, most of the photons behind this diffractive system will route the photons, majority of the photons, to the detector that is assigned to that class. So a max operation at the back end with 10 detectors gives you the class score with this kind of a scheme. These are some test objects never seen before, showing you how it operates. For example, if this is the new handwritten digit 1, most of the photons went to the correct detector at the back focal plane array. And this is number 7, giving you the same thing. Because this is a coherent processor, you can encode information in amplitude channel or phase channel, and at the same time, actually. That's why we tested it with phase encoding on a more difficult task. This is fashion MNIST data set. It's a publicly available data set of fashion products, trousers, sneakers, bags, you name it. So these are after the training, which is a one-time effort. These are some test objects taken from the fashion MNIST data set. For example, if you shine a trouser, most of the, this is the phase encoded information at the input plane. Most of the photons went to the correct detector right here. If you look at, for example, a dress, same idea. So it's all optical inference through encoding of the information through phase and or amplitude, and the solution comes in extreme speed because these are thin optical elements where delta Z between the layers is a few lambda. Depending on how you construct. So these were some examples with the training loss being mean square error. That's why at the output of a correctly classified object, the detector would be having a uniform intensity. That's an overkill. You can actually use another a training loss function like cross entropy, which scatters the field out but still gives you the maximum number of photons for the correct detector. That gives you some significant improvement in generalization performance. For MNIST, you can have 97, 98% classification accuracy. In fact, these days, it's more than 98% with some other additional tricks that I won't discuss today. So diffractive networks have depth feature, which means their inference, classification accuracy, their generalization, their power efficiency, their signal contrast at the output with respect to the other competitor detectors. All of these increase as you build deeper architectures that have one diffractive layer following the other. In fact, one way to think of a diffractive processor is it's a universal linear transformer. You can implement any arbitrary complex valued matrix operation between an input and an output. And let's say, in a diffraction limited fashion, you have Ni pixels at the input and N sub O pixels at the output. If you have Ni and O degrees of freedom, which means the diffractive elements that you have trainable within a diffractive network, if they hit Ni and O, you have beautiful approximation power. For output mean square error, transformation errors, or cosine similarity, you hit a perfect approximation for any arbitrary complex function. But the amazing thing is that if you take any certain budget of trainable diffractive elements, like take a certain x equals something point in here, distributing the same number of diffractive neurons into one layer after another layer beats actually having it only at a single diffractive layer, which means it's an architectural depth that gives you better learning, better generalization, despite the limited learning data set here, which is only 55,000 examples of input-output pairs representing this complex matrix. I'd be happy to discuss more about where is this depth coming from, despite using linear materials. I'll leave that as perhaps a coffee chat or a question. These are some examples of, again, the same feature. Let's look at, for example, this one. You only have 7,200 diffractive neurons that are learnable. And the approximation power is not good here if you distribute them across 2 different diffractive layers, 3.6K in each. However, if you reduce the number of diffractive features that you train with, but distribute them across 4 different layers, 1.6K in each, you learn better, and your approximation errors go to negligible. And you can do the same thing with even deeper architectures and with more diffractive neurons. So one thing that for a universal linear transformation processor, one thing that you might want to say, well, since everything is isotropic, you lose one important degree of freedom when it comes to light, which is polarization. In fact, we've recently shown that you can actually build universal polarization transformers with this system, despite it being basically isotropic. By putting in between a static, non-trainable polarization seed array, which means like the Bayer pattern, instead of the color filters you have there, linear polarizers of different orientations, not trainable, fixed. The diffractive network learns how to communicate with those array of linear polarizers and actually can perform in a single architecture 4 different universal linear transformations assigned to 4 different input-output polarization combinations. Each one of these input-output combinations here is assigned to an arbitrary complex value transformation, and there's nothing birefringent here. Everything is basically standard dielectric diffractive layers that you control the height of each diffractive neuron. You have a beautiful approximation accuracy, but this time, since there are 4 different multiplex channels for 4 different input-output polarization combinations, you need 4 times more neurons. If you look at a standard non-polarizing, standard randomly polarized, let's say, diffractive network, this is the threshold of universal linear approximations, NI-NO, space bandwidth product of the input-output, whereas this one is shifted left by a factor of 4 because of the multiplexing across 4 different input-output polarization combinations. So diffractive processors are very exciting, in my opinion, because they have direct access to phase, amplitude, polarization spectrum of a scene without any pre-processing of information. Unlike other integrated photonic-based accelerators, we do not need to pre-process information. The 3D nature of the wave field is in front of us, and we can access it directly in the analog domain and process it at the speed of light, and the result comes out after a thin material that is structured. So there's so much interesting, exciting aspect of this. You can do quantitative phase imaging with diffractive networks, converting, for example, phase information of a scene into quantitative intensity informations, and many others. Perhaps I'll start the computational imaging side with a single pixel machine vision system that does classification by taking actually spatial features of a scene and encoding them into the spectral class scores, spectral signatures, fingerprint signatures that are detected through a single pixel aperture. Here, we're looking at a diffractive system that does this space spectrum encoding, and different than the previous ones, we're going to be having a single class score, but this time 10 different wavelengths, each of which will represent 1 class of data. And you will be looking at, in the spectral signature per snapshot, which one has the most number of photons, and that's going to be the spectral class score that gives you the classification. In fact, we built this system using terahertz, time domain spectroscopy system. These are the diffractive layers, thickness profiles that were 3D fabricated, assembled, and this is the single output aperture that we were detecting the frequencies that were assigned to 10 different classes. These are some test examples. For example, this one is a 0 and 6 from the test data set, never seen before. And you see here experimental and numerical class scores coming from spectral signatures. Maximum goes to this wavelength, 1 millimeter at terahertz, which was assigned to digit 0. Same with 6, 1.3 millimeter maximum class score from that single pixel. You can also do actually a symbiotic a simple, shallow artificial neural net that takes these class scores and reconstructs them. And there's actually a very nice symbiotic relationship between the image reconstruction neural net and the diffractive neural net, because the backhand can actually correct some of the mistakes that are made in the front end. So this is showing you a good reconstruction, experimentally matching with our forward model, coming from these 10 numbers coming from that single pixel system. You can push the classification accuracy of these kinds of systems, true for the previous part that I've described, through differential encoding of information. Here we're looking at 20 wavelengths at the output, where 10 of these wavelengths are virtually positive class detectors, and the remaining 10 are negative. So based on a normalized differential class score, we get a better actually generalization to unknown data. And in this case, through this single pixel system, using 20 wavelengths, we've achieved approximately 97% for MNIST. You can also scale up the wavelengths. We here used the MNIST data set. And there are 52 wavelengths here, differentially encoding 26 handwritten letters. And we achieved something like 85.6% generalization classification accuracy using these differential 52 wavelengths, giving you 26 class scores through this single pixel. So again, this is a framework that you can build exotic computational imagers that benefit from the fact that you have your hands at the input channel. All degrees of freedom within that input scene is ready to be processed by a diffractive network. Let me give you another example from one of our recent work where we took a diffractive network to see through and trained it to see through and generalize to see through random diffusers. Here the task is you have an unknown object that is hidden behind random unknown phase diffusers, completely hidden. And the diffractive network is trained with examples of these phase diffusers, random examples with a certain correlation length. And we asked it to generalize. If I show an unknown object through an unknown random new diffuser, it should be able to stabilize its image and give you a good approximation to it. So this is actually a system that we also experimentally tested. And the idea is highlighted here. If you don't have anything, you have scattering, diffraction through the unknown phase diffuser. And with the diffractive network, you're creating an image that takes those additional modes created by the phase diffuser, random phase diffuser, and makes them lossy. The key here is to train the diffractive network to solve this imaging problem with sufficient number of examples of random phase diffusers. So at every epoch, we're using something like 20 of these random phase diffusers. Let's say you have 100 epochs of training. You have, there you go, 2,000 examples. And at the end, you want it to generalize to new diffusers with a similar correlation length, but generated new. And the key signature of this kind of a system is that it is going to generalize to image through new diffusers. B here means blind diffuser, never seen before. K means these are the diffusers that were used during the training before. In both cases, you kind of see a convergence. In fact, these are coming from earlier epochs, and that's why their performance is very much like blind diffusers. So because the network forgets the random diffusers that are used in the earlier epochs, and its performance with a new diffuser, entirely new random diffuser, is almost the same as earlier known but forgotten diffusers. This also generalizes to other kinds of structures never seen before. So this is actually testing it with gratings of different periods, showing you basically the period of the test target, and this is the measured period seeing through random diffusers, both known and blind and random, but used during epochs. You get the same generalization. N here refers to the number of diffusers used in each epoch. So if you're going to look at the correctly trained system, you should look at the purple N equals 20. That's the best because it's seen 2,000 diffusers and generalized very well. So if you look at what's going on here, how do you see that? System working? There are actually various interesting features to learn from this kind of a design. If you look at the diffractive layers that are fabricated and their designs, you see a grid of structures like microlenses that are formed and axially aligned from one layer to the other layer to the other layer, surrounded by some high-frequency phase perturbations. These two collaborate together to create an imaging system resilient to random phase perturbations. I'll give you more insights to that in the next slides, but these are some experimental results done in terahertz. This is the 3D fabricated system. There are 4 layers here, hard to see because it's very thin. and one layer following the other. These are experimental results with known diffusers from previous epochs, blind diffusers, and gratings never seen before, nicely matching. Of course, terahertz optics in general is not as advanced as visible, so there's substantial noise here, but the idea is there. This system also works when you change the correlation length. For example, here you're looking at a diffractive network that was trained with a certain correlation length of 10 lambda. But now, and it works beautifully well to generalize, especially look at this row here, n equals 20, 2,000 diffusers being used in the training phase. It generalizes very well, but the good thing is that if I put there a more difficult diffuser, like a 5 lambda, different type of statistics of random phase islands, it still works. It doesn't give you an apple. It's actually trying to mitigate the additional modes that are scattered by these rapid islands. What happens if you take out the diffuser? It works very well. That means it's actually an imaging system with some built-in resilience. So whether it's a blind diffuser or a dynamically changing known diffuser, this system mitigates the perturbations created by these random diffusers. There is depth to the system, which means deeper architectures perform better generalization to unknown diffusers. And this is something that I get all the time asked. How do you ensure that this kind of a scheme that has multiple layers, how do you align it at the wavelength scale? Well, there's some vaccination that you can introduce. Inspired by the pandemic, we call it vaccination of diffractive networks, so that they model the misalignments as part of their training, so that when you train them and when you fabricate them, they get more resilience to on-demand or random misalignments of the system. So let's come back to the islands that I've described. I want to give you a little bit more insight about that. If you design a diffractive imager, an autoencoder, without any diffusers, this is what you get. These are phase islands densely packed. That's how the diffractive network is mitigating diffraction between the layers to create an imaging system. That's the phase islands that take care of the diffraction between the layers and create a nice imaging system. And that's the zoomed in image of a system trained without any diffusers. If you look at what's happening when you train it to see through random diffusers, you see the same densely packed pattern, this time slightly opening up, and there's some random phase perturbations between them. In fact, if you do a study of the locations of those islands, microlens arrays, let's say, they're axially aligned. So they actually are aligned to each other, and that's the backbone of the imaging system. That's how it images if you take out the diffuser. But if you take out the random, for example, phase patterns around these microlenses, you cannot have it work. It's the combination of those high-frequency phase perturbations and the microlens array that is self-aligned axially that work together to design a resilient system that can see through diffusers. So I'll finish off in the last minute or last 2 minutes of my talk with a very exciting recent demonstration of a system that actually images certain classes of objects and erases them, other classes of objects, from the output image. So it's actually a class-specific imaging system. We built a system that you train for it to only image high-fidelity imaging of a certain class or group of classes of objects, whereas everything else is erased at the output for security, for privacy protection, etc. This kind of an imaging system has many loss terms as part of it. Some of it is related to the target class, some of it is related to the other classes of objects, so that you can actually have a good imaging fidelity and at the same time rejection of non-target, non-desired systems. So these are some examples of a 3-layer diffractive system where, in this case, handwritten digit was the target. These are the outputs, and these are showing you the how the objects from other classes are imaged. They're lower intensity, random, impossible to recognize, and these are beautiful images with high intensity and high fidelity. You can do this also with a group of classes. For example, here the network was only targeting handwritten digits 2, 5, and 7, and the rest were erased all optically. This does not capture any image, so it's not invertible because the information is gone. somebody has to have our model to kind of perhaps build a machine learning model to hack it, but from the image itself, it's not hackable. You can do this over a larger field of view, as shown here. And the depth advantage is also coming back here, where if you look at the intensity rejection here for other classes versus the target, you see an important boost, which means these might not even trigger the camera. So they might be just ignored because they're below a threshold, which means this camera starts only recording when the target object of interest is within your field of view. We used also a 3D printed system. These are the 3D printed layers of this 3D diffractive network that we assembled working in terahertz to show you that it actually is experimentally also nicely working. These are experimental results, and these are the other classes that are erased all optically from the output field of view. Finally, I want to also mention this last bit of work, which, in addition to class-specific imaging, brings class-specific linear transformations, which means this one is performing a complex or arbitrary linear transformation between the input and output, but it does that only for a certain class, which means it's encryption that's class-specific, where in this case, the 2 is transformed with a certain transformation matrix. Only if you have the inverse of that transformation matrix, you can bring the images back. But for the rest of the undesired classes, they cannot be brought back because they're scattered, and basically this linear transformation that's achieved with this class-specific camera is also class-specific. To conclude, diffractive networks give us 3 unique areas that we can explore. One of them is building statistical inference engines, partially optical, partially electronic, maybe hybrid, you name it. I think another very rich and exciting area is computational imaging, computational microscopy, and computational sensing. Spatially, at the microscale, nanoscale, there are tremendous applications of this kind of a framework. And finally, I haven't talked about this, but I think for telecommunications and for other applications, if you need a certain box that will do polarization encoding, spectrum encoding, phase amplitude encoding, permutation operations, you name it, that's how to do these kinds of inverse designs through this kind of a black box. With this, I'd like to conclude, and thank you very much. Go ahead, Yoav.
Hi, Erdogan. Very nice talk. I have a question. I think maybe I missed something. I think that in neural networks, one of the strongest parts of the merits of a neural network generally is a nonlinearity after each layer. So there's a linear operation, and then the layer has some kind of an activation function, and then it goes on again for the next layer. My impression is that these architectures do not have a nonlinearity in any layer. So what are the implications of that? And if there are any plans of making a nonlinearity in all optical system that has some kind of a nonlinearity, I guess it will require some light-matter interaction that will slow it down, if you can refer to that issue.
Great. So yes, universal approximation would require one form of nonlinearity, and within a single hidden layer, if you have sufficient nonlinear nodes of different kinds of nonlinearities, it gives you an error bound with enough of these nodes working. This system only has the nonlinearity in the current version that I'm showing at the detector array. That's where you have the electric field intensity. There are different ways to bring nonlinearities to this system. You can use nonlinear optical materials, metamaterials of various different kinds, exotic structures that can actually use a pump beam to change the refractive index, temperature, or other nonlinear processes built in. So you can do that. There's a cost associated with that complexity and the low power of, in general, nonlinear processes. Going back to the implications of a diffractive system that is linear except the detection system. It doesn't change anything. It's a linear universal transformer. It does any arbitrary complex valued transformation between an input field of view and an output field of view if it has enough degrees of freedom. It's a universal linear transformer. For tasks that are hard to define with a certain equation, what is a cat? I don't know. I can only learn that through data. There I see limitation. For CFAR 10, as an example to benchmark, the best diffractive, single diffractive layer is about 62% today in my lab in terms of its classification, whereas it's 90 plus for a deeper convolutional neural net. So that gives you an approximation gap because of that architectural limitations. However, diffractive networks are still deep because if you give me a capital N diffractive neurons that I can engineer with, the question of depth is, how do you want to create the architecture? Let's consider two cases. One, very shallow, single layer. I put all of the diffractive features on a single layer versus 5 layers. I divide that N by 5, N over 5, N over 5, 5 layers. The second one learns better, generalizes better, is more photon efficient with the same training data, with the same number of epochs, period. Why? Because input seen communicates through modes. Those modes are very weak for high NA, NA directions. As a result, a single diffractive, shallow diffractive layer to create a universal linear transformation will need to amplify those so that the ballistic photons can be on the same order of magnitude. Since amplification isn't there, what do? The diffractive system, through deep learning-based optimization, dampens the central lobes and creates a hole burning. Effectively, it doesn't utilize your capital N diffractive neuron budget. It kills it. There are numerous examples of it. That means architecturally, diffractive systems, when they process the input scenes field, a complex field, polarization, spectrum, they like to work with deeper architectures because they can solve complex puzzles. What's a puzzle? Solve this spatial loss function with this diffraction efficiency penalty and also penalize other objects that I don't want to see. Many things at the same time. And that's when depth really shines.
Yes, okay.
Thank you.
Sure.
Quick question. So I'm sort of reminded, I'm sure you're aware of Kevin Wagner's work from the 1980s on adaptive neural networks, optical neural networks. And one of the things, this is when I was working on my PhD, and one of the things that was realized is because computation sort of started catching up with Moore's law, and there was tremendous progress on that front, the idea of committing an architecture and hardware to a specific task became sort of less and less attractive because you could use computational networks to change things all the time. I'm trying to understand the trade-off. There's the beauty of doing this, of course, what you're showing here. But your 3D printed layers are committed for life, right? They're not going to change over time. So can you just comment on that?
Great question. A microscope is designed and is committed for life, right? You have an objective system and it doesn't change. So if you want to do computational imaging on the fly, you don't change the microscope. It's supposed to be there. This is a good example of an imaging system. It does a certain thing. It erases other objects, or seeing through random diffusers. This one. This is supposed to be an imaging system, and the objects change. So whether or not here the diffractive network changing is irrelevant because, let's say you're talking about human tissue and you want to image something implanted under the human tissue. There's blood flow and you model that random phase perturbations or amplitude perturbations and everything. We are humans. We don't change. That tissue remains within the same statistical, scattering. So that means the imaging system, if you're targeting a microscopic imaging, macroscale imaging, that's perfectly fine to have a static system. When it comes to a changing data stream, processing, inference, the question is, yes, being static is a big disadvantage compared to a GPU or other kinds of things that we can do with our smartphones, right? That is true. However, think of an application where you cannot afford to digitize. Let's say you need only one task. Is this a human? Is this a human or not? Is this a human or not? Is this a missile or not? I want to do this a million times a second, and I want to do this across 1,000 places, in my base station. That's too much of power. That's too much of data. This kind of a scheme can perhaps be a simpler yes or no trigger. It may have a lot of false positives, etc. But you can bias it such that other pipeline of workflow of processors can help it. Of course, this is not a replacement for a GPU, will never be. But there are certain applications where its power efficiency and speed of computation becomes very crucial, perhaps.
What about the fact that you can process a coherent wave and not just the intensity?
So I didn't get the question, but these are coherent processors, but they can also be converted to incoherent processors, which means...
It's another advantage of what you do. I mean, compared to a computer, which will process intensity, you can process coherent rate.
Yes, so that's actually exactly highlighted here where I was saying, for example, here on this slide, that was exactly for coherent information processing, as an example, phase retrieval is very costly. You don't need to do this, so you can have it. But going back to, since you mentioned coherent, diffractive networks are not obliged to work with coherent systems. They can also be incoherent, so you can actually broadband, spatially and temporally incoherent processes modeled and work with diffractive networks. Are they as powerful as coherent networks? No, because coherent networks are really very powerful because of the additional degrees of freedom that they have. But this system can work with incoherent and broadband light as well. But pre-processing of information is actually what I was trying to say. Some things are in your field of view there. Take, for example, the phase information. There's some phase information that is what you want to sense. A threat of one kind. I don't know, a bacteria growing somewhere, okay, which is a phase object, right? So if the phase information is there, a traditional microscope will have to do phase retrieval first using GPU. This kind of scheme actually doesn't have to do that because it can act on the phase channel directly.
All right, so I think we should move on. Let's thank our speaker one more time. And there will be extra time for Q&A at the coffee break, for sure. With that, I'll pass it off to the next session to Praneet.
Right, so I'm Praneet Chakravartula. It's a bit of a tongue twister name. But we had the stage set for this session in the morning keynote that spatial computing and computational imaging, along with computational displays, is becoming very important. And we have a bunch of papers in this session that deal with exactly this. Holographic displays and etendue expansion for holography. And so the first paper is going to be analyzing phase mass for wide etendue holographic displays. The paper is authored by Sagi Monin, Aswin Sankaranarayanan, and Anat Levin from Technion, and the speaker is Sagi Monin.
So, hi everyone. In this talk, I'm going to theoretically analyze the etendue expansion of holographic displays by adding a static phase mask, including their limitations and optimal designs. But before we explain etendue, let's see some of the amazing advances holographic displays have seen in the recent years. Such features such as correct focal cues, large field of view with small form factors, and real-time content generation. But although all these tremendous advances, holographic displays still suffer from limited etendue. So holographic displays are usually based on spatial light modulators, which modulate the phase of incoming light. The SLM has two main physical properties, its size and its pixel pitch. When the SLM is illuminated with a plane wave, it can tilt the wave with the maximum angle inversely bounded by the pixel pitch. In practice, high-end SLMs today can only tilt light by ±4 degrees. In near-eye holographic displays, we assume the viewer places his eye adjacent to the SLM and views the target image presented by the SLM. The size of the viewed image is the field of view of the display, dictated by the maximum angle the SLM can produce. And the eye box, which is where the viewer can place his eye and see the content, is proportional to the size of the SLM. Now, the multiplication between the eye box and the field of view is known as the etendue of the display, and it can be shown that the etendue is solely governed by the number of pixels in the display. Now, by adding lenses between the viewer and the SLM, we can control the field of view and the eye box. However, increasing one property decreases the other, meaning that the etendue is invariant to changes in the view optics of the display. So ideally, holographic displays would like to achieve a field of view of approximately 120 degrees and an eye box of 1 centimeter. However, supporting both these ranges requires a huge etendue, requiring that we increase the number of pixels by 3 orders of magnitude. So previously, researchers have suggested that etendue can be expanded by adding a static phase mask, or a diffractive optical element, a DOE, in front of the display. By adding a random mask with a pitch size smaller than that of the SLM, the light scatters to larger angles, increasing the field of view without changing the eye box. In this work, we suggest analyzing etendue by a slightly different approach, relying on the fact that the angular range is not determined by the absolute phase, but by the slopes of the DOE. So, if we illuminate our SLM with a plane wave, we can generate an image of a certain size. Now, if we tilt the plane wave at an angle, we can generate an image of the same size at a different part of the field of view. However, if we can illuminate with a wavefront mixing multiple tilts, we can display a large field of view, increasing the etendue. So, we think of our mask, our DOE, as a mask that locally tilts the illumination on the SLM. So, by adding a DOE, we can increase the etendue, but the number of controllable pixels of the SLM did not increase, leaving us with the same number of degrees of freedom. Leading us to the question, what are we trading etendue for? So in this work, we offer a thorough theoretical analysis of DOE masks and address the following questions. What are the images we can generate with such a display, and what are the prices we pay? Next, we study how do we evaluate our DOEs and what is our loss function. Finally, we ask what is the optimal shape of our DOE. Previous works relied on random masks, but is that the best we can really do? So in order to answer these questions, let's start by reviewing how SLM content is designed. In our work, we rely on the framework of Attal, where the observed image is generated in the Fourier transform of the multiplication between the SLM and the DOE mask. So, given a target image and a fixed DOE, you optimize a phase mask to display in the SLM such that the magnitude of its Fourier transform best approximates the target image. So, given this cost function, we ask, what is the best design for the fixed DOE? Now, to facilitate this analysis, we consider DOE of the following family. We divide our DOE to patches of some size and assign inside each patch a constant tilt, which is depicted here by an arrow. To better visualize the different tilts, we assign a different color to each tilt. Note that in practice, as the target image is in the Fourier transform of the SLM, each tilt generates content at a different part of the field of view. Now, by reducing the patch size, we can approximate our random DOEs, which were considered in previous works. So now that we understand the image formulation, let's analyze what penalty we pay for etendue expansion. And we start with contrast penalties. So, as mentioned earlier, the SLM can generate content over a small field of view. The added DOE sends light to a larger angular range, but does not increase the number of degrees of freedom. So we expect for some limitations in the ability to generate content. In the paper, we prove the following claim. We can approximate any desired target image, but if we increase etendue by a factor of x, we pay a price of contrast or SNR of a factor of x. Here's the image we generated with this target. We kind of got what we wanted, but the solution is very noisy. Our claim is based on the use of random masks, and in the paper, we showed that contrast reduction is inherent with random masks. So we've seen that etendue expansion can come with a large penalty on contrast images we can display. Next, rather than sacrificing contrast, we try to trade etendue with the resolution of the target image. So this approach, suggested by Attal, is as follows. We attempt to display a wider image, but maybe we can do with a blurred version of the image, effectively reducing the number of entries in the target image. To model this mathematically, Attal suggested adding a low-pass filter to our optimization problem. So, given this low resolution cost, we start by empirically evaluating a few choices of DOEs. As we said, we use DOEs with patches of constant slope, and here we test the effect of the patch size. Here's our target image, and the red frame marks the original field of view of the SLM. Here are the reconstructed images. Our solution is still not noise-free and suffer from reduced contrast. We see that, as stated earlier, random masks in very small patches suffer from very, very low contrast, and we can also see that contrast improves as we increase patch size. Now, to understand why wider patches achieve better contrast, we recall that different tilts generate content at different parts of the field of view. In the paper, we explained that with large patches, all the content of the one target of the image is generated by a big continuous region. This is equivalent to a low-pass filter. On the contrary, random masks convolve the target with noise, introducing speckles which reduce contrast. Now, based on our simulations and further analysis, we derived the optimal shape of our DOE, a quadratic phase mask. This leads us to our next claim. Given the optimal DOE, we can find an SLM assignment for which we achieve a factor X etendue expansion in the price of no worse than factor X resolution reduction. So we've seen that expansion in etendue can be translated to equivalent penalty on contrast or resolution. And we've seen that random masks come with reduced contrast. And if we want to trade etendue for resolution without losing contrast, the optimal DOE, we can use the quadratic phase mask. We move on to our next question. How do we evaluate our DOE? So far, we aim to generate 2D target images. But if we carefully inspect our optimal DOE, we find a flaw in the design. So to understand the flaw, we note that our optimal mask is actually a lens. But it is well known that lenses do not increase etendue. So what is the problem? The cost function we used effectively assumed that the pupil of the viewer is as wide as the eye box and simply integrates over all of it. But if the pupil decreases a bit, not all light rays are integrated, and if we use a quadratic DOE, we effectively get that some of the image content disappears. Now, if the viewer shifts his eye along the eye box, content at the different image regions appears and disappears. We received this result since we optimized over an inadequate score, which considered only the formulation of a single 2D image. This means that we should evaluate scores that take into account 3D content and take into account the pupil location inside the eye box. So we concluded the 2D costs lead to problematic results, and to do better, we optimize for target light field image. We optimize for a target light field image, and here's the animation of the optimization result. Now, the viewer can shift his eye along the eye box, and the entire field of view is continuously covered, and the occlusion between the two objects is updated properly. Here is the eye box, and we mark with 4 different colors, 4 different positions of the pupil, and 4 corresponding light field images we want to see in these positions. Now, as with 2D target images, we simulate DOEs with different patch sizes and see a similar trend where image quality increases with patch size. We showed that there exists an optimal DOE for a light field target image, and perhaps unsurprisingly, the optimal mask is a lenslet array with each lens as big as the pupil. This solution might look a bit familiar, as lenslet arrays are traditionally used in integral displays, but there's a big difference between these solutions. In our approach, the image is formed in the Fourier domain, hence the numbers of lenslets is quite small and determined by the number of viewpoints. In integral displays, the number of lenslets is determined by the number of pixels in the target image, which is quite large. So we saw that evaluating the light field supported by a candidate DOE is a good way to ensure that we actually expand etendue. In the paper, we additionally explore focal stack targets. We also shown that the optimal shape of our DOE. When considering 3D costs, the optimal DOE is a lenslet array in this Fourier space. We have also shown that random masks are not a good choice, as they result in inherent contrast reduction. Now, this summarizes my talk about analyzing the theory of etendue expansion. And with this understanding, we ask, can we do something better than a static DOE and increase etendue with a programmable mask? So stay tuned for my next talk of exponentially-wide etendue displays using a tilting cascade. Thank you for listening.
Right, so we can either take questions now or wait until the next talk and ask collective questions. Right, we'll take questions.
I just had a quick question. Can you comment on how the etendue is still increasing if we're using a lenslet array in Fourier space?
So basically, we can still see the field of view in each position of the eye. The entire field of view want to increase, and the eye box did not reduce.
So does each lenslet still have like the same effective NA as like one big lens would have, or?
Yeah, so exactly. They have the same NA with one big lens.
Okay.
Okay, now that you're asking questions, I had a question too. When you're doing the light field sampling, you're dividing the SLM into discrete regions, and each of the region is going to produce a light field target image, right?
Yeah.
And if you look at the iBox, your iBox is your projected virtual SLM, and your pupil is sampling these discrete regions. Now, if a pupil samples a region where half of the pixels fall in one target light field and the other half, then there's going to be light field crosstalk.
Yeah.
So, and this can be remedied only if you do a continuous light field sampling. Can you comment on the sampling and the crosstalk?
Yeah, so thank you for the question. So actually, we do oversampling of twice. So actually, if you just move the eye by half a lens, you can still see, you see another image. So that takes care about on the crosstalk between the lenses.
So you sample?
Yeah, we oversample it.
Well, the next talk is also from the same speaker, so.
Yeah. So, hello again. In this talk, I'll present a method and a prototype to increase etendue of holographic displays with a programmable phase mask without increasing the number of pixels, opening a new approach for designing holographic displays. So, as we saw in my previous talk, most common holographic displays are based on spatial light modulators, which modulate the phase of incoming light. Now, the SLM has two main physical properties which dictate its capability to act as a display, its size and its pixel pitch. The maximum angle at which the SLM can tilt light is inversely bounded by the pitch. In practice, existing SLMs today can only tilt light over small tiny angles of plus minus 4 degrees. Now, the multiplication between the SLM size and the angular extent is known as the etendue, and it's proportional to the number of pixels in the SLM. So, ideally, holographic displays would like to achieve a field of view of 120 degrees and an apex of approximately 1 centimeter. Unfortunately, supporting this etendue requires a display with 1 billion pixels. This is 3 orders of magnitude higher than what's available today and is unrealistic. Even if such a display can be built, handling both the electronics and content generation for 1 billion pixels would be a very difficult problem. In this work, we want to increase etendue without adding pixels. Now, if we examine our setup and illuminate it with plane waves coming at different angles, we can generate images at different parts of the field of view. This means that effectively, by introducing different tilts to generate pixels, we can change the angular range of our display. We suggest building pixels whose can tilt, increasing the etendue of our system. We build a prototype of tiltable phase modulators and demonstrate some of its uses. So, ideally, we do want an array where each pixel can tilt independently over a continuous range of orientations. This is known as a tilt-tilt micromirror array. Such devices have been demonstrated, but they're still at research-grade prototype. What can be built more easily is an array of binary tilt pixels, where each pixel can tilt independently into 1 or 2 orientations. So notice the difference between the continuous and the binary tilts achievable by each of the systems. In this work, we show that by combining multiple binary panels, we construct a device implementing a large range of tilts. So, to generate a wide angular tilt, we build the following setup. We start with a piecewise constant SLM, and by programming its phase of the pixels, we can emit light within a limited cone. Now, let's trace the light coming from 1 pixel. Using a fourth system, we relay that pixel into another panel implementing a binary tilt. Now, by tilting the pixel either left or right, we can double the angular cone of that pixel. By relaying our output to an additional binary tilt panel, we can further double the angular extent of that pixel. As each layer doubles the angular extent, the full angular extent is expanded exponentially with respect to the number of layers, meaning that by combining a relatively small number of layers, we can achieve a very wide etendue expansion. So this was the basic principle of my system, and now I'll explain how we realized it. So as we aim to generate binary tilts, commercially available binary digital mirror devices are ideal candidates. However, their angles are fixed to plus minus 12 degrees, which is too large. Instead, we implement binary tilts with polarization-sensitive gratings. We use liquid crystal display, which is traditionally used to modulate either the intensity or phase of light in a less traditional manner. We use it to rotate the polarization of each pixel independently. We combine this LCD with a polarization-sensitive grating, which tilts the incoming light into one or two angles, depending on its polarization. So consider the following setup, and where the light originating from the LCD encounters a 4F system with two polarization-sensitive gratings in between the lenses. Now, depending on the light's polarization, when it encounters the first grating, it is either tilted left or right, with the second grating tilting it back to its original angle. This effectively shifts the light in the Fourier plane, introducing tilt in the image domain. Now, by controlling the distance between the gratings, we can control the size of the angle we want to introduce. So, this combined 4F system with two gratings and an LCD is our binary tilt layer. Our full prototype consists of a standard piecewise constant SLM and two binary tilt layers, where we control the tilt angle by changing the distance between the gratings. Here is our experimental setup in the lab, and the different parts of the system are marked with different colors. In our setup, we demonstrate etendue expansion of a factor 4 along the horizontal axis. But before I show you some of our experimental results, let's review how we form a holographic image. Assume we're interested in generating some target image with the original field of view here marked in red. The target image we aim to generate is 4 times wider in the horizontal axis. We start with a tiltable display and divide it to patches. Each patch tilts all pixels in the same direction, generating content at a different part of the image. Now, after assigning different tilts, we optimize for a phase to display on the piecewise constant SLM, such that the generated wavefront produces the desired target image. I will now present several results of our display. So we start with two holographic images. We divide the piecewise linear modulator to patches and calculate the corresponding SLM pattern and capture our image. We also use our display to validate the theoretical predictions of my previous talk and test the effect of patch size. As we can see, we achieve better contrast with larger patch sizes. In our experimental results, we can see our system is more susceptible to the patch sizes than in the simulations. This can be explained by the fact that the smaller patches are more sensitive to optical aberrations. So to better visualize the contrast difference, we present here a cross-section of the snake's tail in real and simulation captures. We also show the ability of our system to generate more complex content, showing a 2D panoramic image. Now, one advantage of our system is that we can adapt the slope assignment based on the target image. For example, let's examine this following scene, where the luminance of the target image is not evenly spread. Remembering the different slopes generate content at different parts of the image. Here, we visualize the result with uniformly distributing the different slopes, sending equal amount of light to each quarter of the image. However, since the target luminance in these quarters is not uniform, the resulting images suffer from artifacts, such as light leakage and disappearing background. Notice this is true for both experimental and simulation results. Now, by adapting our slopes, we can remove these artifacts. We first calculate the energy distribution in each quarter of the image. Then, we adapt our slope assignment based on the target image distribution. In this example, 89% of the energy resides in the green quarter, so most of the SLM area is assigned to that corresponding tilt. Here are the results of the adapted images, and as you can see, the images suffer from much fewer artifacts. So, as with other holographic displays, we show the ability of our system to present a 3D focal stack target. We show here two cars presented at two different planes, and as the camera focuses between different planes, we can see one camera in focus and the other one is out of focus. So far we've discussed the use of our system as a near-eye holographic display with increased etendue. In this case, the SLM is used to generate wanted content at some virtual plane away from the SLM, and the viewer focuses on that plane to view the image. However, near-eye holographic displays are just one of the uses of SLMs. A different approach is to use the SLM as a multi-view display. In this case, the eye directly focuses on the SLM, and by shifting the viewer's viewpoint, he views different images. We show the use of our system as a multi-view display with spatial multiplexing. To display spatial multiplexed images, the SLM is divided to hoggles, which are groups of multiple pixels, demonstrated here by green squares. We assume that the eye resolution is limited, and the viewer can only resolve aggregation of multiple pixels, which are the size of the hoggle. After dividing the SLM to hoggles, each hoggle presents a different diffraction pattern, directing light to a different direction, resulting in multiple images. Here are some results captured by our system. The first row shows the captured images of our display, and the bottom row shows the simulated images we aim to display. On the right, you can see the pixel tilt assignment. So, our current prototype containing 2 binary tilt layers and a phase SLM is quite bulky. The reason is it's based on imaging each LCD into the next one with a 4F system. We propose 2 alternative future reducing size of our current setup. The first is to remove the 4F system and simply concatenate the LCD to the grating. In this manner, we can chain multiple binary tilts layers without the need of optics between the LCD, greatly reducing the form factor. This would require customization of the grating layers to implement the exact desired tilt. While for our prototype we were not able to find off-the-shelf gratings with the desired tilt, this customization is doable. The second approach is to use a tilt-tube micromirror array, reducing our system to a micromirror array and a phase SLM. While existing tiltable micromirror arrays do not have the desired number of pixels, in the paper we discuss how they can still be used to allow for some constrained form of etendue expansion. So, to summarize my talk, in our work we suggested a method of increasing etendue without increasing the pixel count, a prototype implementation of this method by successive binary tilt layers. We've shown that exponential increase of etendue with respect to the number of binary tilt layers. And we demonstrate the usage of a tiltable phase modulation for different applications, such as near-eye holographic displays and multi-view displays. Thank you for listening.
Questions? Okay, one simple question. Can you comment on, it looks like you, right now you have your tilt layers, and then based on your tilt, you're optimizing for the hologram.
Yeah.
Can you comment on some joint optimization strategy? Or?
Yeah, okay, thanks for the question. So we actually tried joint optimization, but as I mentioned before, the system suffers from optical aberrations, which increase when we use very small pad sizes. And when we do joint optimization, it results in very small pad sizes, so the displayed images weren't that great. So basically we had to optimize them one after the other.
You know, we're running short of time, but also I had one thought looking at the result. Looks like some of the speckle noise that you see is probably because, the light that's reaching from multiple tilt layers aren't reaching the same image pixel in phase. Right, so it's out of phase, which is causing a little bit of speckle. Have you thought about having, some kind of phase compensation to make sure, light from different tilt layers are reaching image pixel in phase that might reduce some of the noise?
Yeah, so we haven't tried it to basically fix all the aberrations. We did try several approaches, but that we didn't try. But yeah, that might help achieving better images. Yeah, very good idea.
Right. You have a question? Okay, last question.
Thank you for the talk. Quick question. The loss of contrast, is it in any way related to loss in spatial resolution as well? Because you are dedicating parts of the phase SLM for each direction.
So can you repeat the question?
Is there any relationship between the loss in contrast ratio and possible loss in spatial resolution?
So you do get images with more noise, and when we deblur them, we get loss of resolution, but there's not a direct link that we found.
Thank you.
Okay, so thank you. So the next speaker is Benjamin Attal. The paper is going to be towards mixed state coder diffraction imaging. Benjamin. Thank you.
Hi everyone, I'm Ben, and today I'm going to present my work towards mixed-state coded diffraction imaging. There exist many computational techniques for microscopy that can capture the complex valued optical field of a specimen, and these fields are defined by an amplitude and a phase, where the phase carries useful information about a sample, such as thickness. However, conventional sensors can only see the intensity of a field. Coded diffraction pattern imaging, or CDP, is an example of a computational technique that can reconstruct both amplitude and phase from a set of intensity-only diffraction images. CDP was originally used by the X-ray community, but can also be used for imaging with visible light as well. However, coded diffraction imaging typically assumes that the optical field is coherent. This is not always the case in practice. For example, it's well known that broad bandwidth X-ray beams can affect reconstruction quality in coherent diffraction imaging. Mixed-state algorithms have been proposed to computationally account for non-ideal sources by modeling the radiation as an incoherent combination of multiple wavelengths, or in other words, as a mixture of several coherent states. In this work, we aim to extend coded diffraction pattern imaging to handle mixed-state fields. In particular, we demonstrate multi-wavelength reconstruction with our framework. And in this context, we can leverage compressive priors to perform reconstruction with fewer measurements than coherent techniques, even achieving color reconstruction from only a single image. We also analyze the behavior of our mixed-state CDP framework and show that it's more accurate than other methods under high amounts of read noise. And finally, we demonstrate the utility of mixed-state CDP by applying it to optical path difference measurement. Before diving into our method, we'll discuss CDP with coherent lights in more detail, starting with an example imaging system. So in this system, we first illuminate a sample, such as a microscope slide, with a coherent laser light source. The resulting optical field propagates to a spatial light modulator, or SLM, which applies some modulation pattern to the field. The field then propagates from the SLM to the camera, and the camera measures intensity. This is all governed by an image formation model that consists of a number of parts. So first, we start with the complex field leaving the sample, represented by this vector u. We apply a linear operator to propagate the field a distance z1 from the sample plane to the SLM plane, and multiply the field entry-wise by this SLM pattern. We then apply another propagation operator, mapping the field from the SLM to the sensor, and take the squared amplitude of the field at the sensor to produce our intensity image. Finally, we can repeat this procedure for k different patterns. And given our known image formation model, our goal now is to recover the original field by minimizing the mean squared error between the captured measurements and the measurements predicted by our model. In this work, we reconstruct the field incident on the SLM, which can be digitally refocused to the sample plane as a post-processing step. To solve this objective, we can make use of well-studied optimization procedures, such as the popular Gerkberg-Saxon algorithm, which is both memory efficient and fast, or Werdinger gradient descent, which supports arbitrary reconstruction priors and can achieve better image quality, but is less efficient. But so far, we've assumed a coherent model for imaging. This assumption does not always hold, and decoherence that breaks this model can arise in a variety of ways. A light source might consist of multiple distinct wavelengths. The sample might vibrate and change rapidly during the sensor's exposure. Or the sensor might average a field over the area of larger photodiodes. In all of these cases, we can model decoherence as a state mixture of several coherent optical fields. And in this paper, we focus on the multi-wavelength setting, where our state mixture consists of amplitude and phase for each wavelength. So how can we modify our image formation model to account for these state mixtures? Really, there are only a few changes that we need to make from the coherent case. First, we track multiple fields as they propagate from the sample to the SLM to the sensor. And for each image, the sensor now sums the intensities of all incident fields, rather than recording the intensity of just a single coherent field. To summarize, the main differences between the mixed state and coherent image formation models are as follows. In the mixed state case, The forward operators can be state dependent. For example, a phase SLM imparts different phase shifts for different wavelengths. Additionally, the measurements that we capture are a sum of the intensities of all states. So one might ask, can we recover each individual field from these mixed state measurements? And the answer, as it turns out, is yes. We can solve an optimization problem similar to coherent CDP to recover these mixed states, again by minimizing the reconstruction error between the captured measurements and the predicted measurements to recover the unknown fields U sub j. But why not just filter light and perform coherent CDP? We could, for example, sequentially reconstruct each field if we have control over illumination. For other applications, we can also use Bayer filter arrays to disentangle the intensities of each field. So there are a couple of reasons why we might not want to use these coherent alternatives. For one, as we will show, we can make use of compressive priors to recover mixed state fields with fewer measurements than coherent alternatives. Additionally, filtering light is wasteful. If we don't filter, then our system may be more robust to noise. We first demonstrate that our mixed state CDP framework can reconstruct multi-wavelength fields with fewer measurements than coherent alternatives. To experimentally validate our reconstruction framework, we make use of a practical CDP prototype consisting of a laser light source with 3 distinct wavelengths, a phase spatial light modulator, and a machine vision camera, all without any filtering optics. In this first example, we are able to recover a multi-wavelength field using 24 images, while the field sequential baseline requires twice as many images for comparable performance, and fails given the same number of images as our approach. To achieve reconstruction with even fewer measurements, our insight is to use a compressive mixed norm prior designed specifically for mixed state fields. So consider a mixed state field produced by a single object or sample. If we refocus the field to the plane where the sample is located, then intuitively the following should hold. The gradients for this field should be sparse, and additionally, the gradient should be aligned across different states. In practice, we implement this mixed norm prior as a slightly modified total variation regularizer, and use this prior during reconstruction with our Werdinger gradient descent procedure. Here we demonstrate reconstruction using our mixed norm prior with 3 images total. Again, we are capable of reconstructing multi-wavelength fields with higher fidelity than the field sequential baseline. We are even able to perform multi-wavelength reconstruction with just a single image, achieving single-shot color sensing. Note that we recover both the amplitude and the phase for all wavelengths here. Next, we analyze the behavior of mixed state CDP under signal-independent Renoise. Here, we first make a linear approximation of the mixed state image formation model that we discussed earlier. And using a similar derivation to Schechner et al., we show that the reconstruction error depends on the singular values of the linear approximation. On average, the mixed state CDP linearization has a larger response to its inputs than coherent CDP, since mixed state CDP does not filter light. This suggests that under the right conditions, mixed state CDP is more robust to Renoise. We refer readers to our paper for more details. We validate this behavior in simulation for an optical setup similar to our practical prototype. In particular, we reconstruct a multi-wavelength field with a stack of 12 diffraction images. On the left, we show the reconstructed field under high read noise for mixed state CDP and 2 coherent variants whose quality is noticeably worse. And on the right, we show quantitative performance of all methods under various amounts of read noise. Here, mixed state CDP outperforms both coherent variants under high read noise, while performing similarly in low read noise regimes. Finally, we demonstrate the utility of mixed state CDP with an example application of optical path difference measurement. In this application, we simultaneously reconstruct the fields at 3 different wavelengths, and then combine these fields via synthetic wavelength holography to recover an unwrapped phase profile. Above, we show the result of this procedure applied to a 150 millimeter lens. Despite its benefits, our method is not without limitations. In particular, our noise analysis is currently limited to signal-independent read noise. We do not analyze photon noise or phase noise imparted by the modulator. Note also that we did not consider broadband illumination in our experiments, where the source has a continuous set of wavelengths rather than a discrete set of wavelengths. However, we also believe that broadband sensing may be feasible with additional reconstruction priors, or with a combination of optical filtering and mixed-state CDP. Finally, our mixed norm prior only works with memory and efficient gradient descent, though further engineering here could improve performance. In summary, we've presented our work towards mixed-state coded diffraction imaging, which we hope is a step towards more practical usage of mixed-state methods for coded diffraction imaging, as well as a step towards future work that explores mixed-state methods for other forms of decoherence, such as polarization, broadband illumination, and fast-varying samples. Thank you for your time.
Questions?
Hi, thank you for your talk. This is my first time hearing about coded diffraction imaging, so could you help me understand the optical setup? Like, is it an imaging system or just propagation?
Can you say the last part one more time?
Is it an imaging system with lenses, or is it just propagation?
There are no lenses. It's a lensless system. It consists of laser illumination, in this case with 3 different wavelengths. Sorry, I need to find the setup. A spatial light modulator, which in this case is a phase spatial light modulator. A beam splitter, to make the setup compact, and then this sensor, which is lensless in this case.
I see. So the SLM is in reflection.
Exactly. Yes,
Okay.
it's in reflection mode. Yeah. Yeah, absolutely.
Somewhere you were comparing your results against Bayer filters.
Yes.
Did you look at the spectral response of the Bayer filters to decouple it? Or were you looking at the raw? Because typically when we use a Bayer filter for holographic imaging, we know the filter's response function.
Yeah, right.
Sweep monochrome wavelengths and use that information to decouple the measurements at each channel to create a bunch of processed holograms at different wavelengths. And if you do that, reconstructions become in a single snapshot from, partially coherent fields.
Yeah.
Bandwidth become very robust.
Sure.
Just so the question is well communicated. The question was if the authors have looked into the spectral response of the Bayer filter when it came to the Bayer filter-based reconstruction using the color Bayer filter. Right.
Right. Yeah, that's a great question. And so I think I'd like to just point to this result again. So in this case, we are in simulation using Bayer filters, which we've designed the spectral response for to exactly correspond to the 3 wavelengths that we're using. And in this case, because these Bayer filters are letting in less light for each pixel, under high read noise, this reconstruction performs worse than the mixed state technique, which is absorbing more light for each pixel, right? Yeah.
Into account crosstalk, because every Bayer filter is broadband, right?
Sure.
So that means every channel has a bit of everything.
Sure. Okay. Right. No, we're not taking into account crosstalk in this case. Okay. And so if you did take into account crosstalk, then you would have to modify your image formation model to account for the spectral response. But we're not doing that. Yeah.
For actual measurements, that's what we learned to do. You take a monochrome sensor, monochrome illumination source, sweep it.
Yeah.
Get that response.
Right.
That's your lookup.
Yeah.
To decouple your measurements so that what goes into your multi-wavelength reconstruction comes from that decoupled channels.
Yeah, that makes sense. But in that case, it would become a mixed state method if you wanted to handle those broadband spectral responses. So we're not considering that here. Yeah.
Well, we'll take one last question.
So you mentioned that you handle only discrete coherent wavelengths.
Yes.
And you said that if you perform filtering, you need more measurements to get the same quality.
Yeah.
So if you were to go to incoherent set of wavelengths, why would you not do something like interferometry, like ROCT, to
Yeah, I think it depends on the application. So I think one nice thing about these mixed state methods is that these are very general reconstruction procedures. It just, you're computationally, you're reconstructing all of these mixed states from these mixed measurements. And I would say that broadband is not out of the question here. You can still approximate your broadband source with a set of discrete wavelengths. It becomes more challenging as you increase the number of samples you're taking of that broadband source, and you might need additional priors for reconstruction there to better constrain your reconstruction. But I don't think that broadband sensing is out of the question. But that's definitely a great point that for other applications, interferometry might be more suitable.
I see. Because from my experience, even if you do discretize such a broadband spectrum, you need to do it at extremely fine resolutions. Sure. Otherwise, it decorrelates over a small.
I see. Okay. Yeah. That's something that I think we'll need to consider more in future work then. But thank you so much for your question. Yeah, thanks, Ankar.
Okay, so the next thing would be spotlight presentations. Right. While we set that up, I'll use my privilege as the session chair to ask one more question.
Yeah.
I have never seen phase reconstructions to be so smooth as the reconstruction that you've shown here. What have you done? Because mostly the Gershberg-Saxon or even gradient descent almost always results in noisy phase.
Sure. Yeah. So I think that the mixed norm prior is really, really important here, and this is enforcing smoothness and sparse gradients for both amplitude and phase at the sample plane. So this is a prior that's applied to the complex field at the sample plane, both amplitude and phase. So that's contributing to the
But did you have to consider some kind of prior information about, say, your sample or something like that? Because, this kind of smoothness in phase is...
Right. So we assume that we know where the sample plane is. We're back propagating the reconstructed field from the SLM to the sample plane. But that's what we're assuming. Yeah.
Okay.
Okay. I'll grab my...
All right. Let's thank this.
Oh, sorry.
We'll take care of it.
Sorry, just a technical mishap. I think I'll just play it from here. It's not downloading, so I'll just play it from here. I don't know why.
Just do it.
Okay, so these are the poster spotlights. So these were we have 2 spotlight sessions today and tomorrow, but these are the ones that will be presented this afternoon. So these were the top posters that were submitted as decided by our poster chairs. And so, yeah, we'll play through them, and then afterwards we'll go out to the poster session. So...
Single photon structured light. Structured light 3D imaging has inherent trade-offs balancing acquisition time, precision of scan, and robustness to high noise regimes. For instance, certain techniques achieve high depth resolution by projecting multiple patterns, but necessitate long acquisition times. In contrast, techniques projecting a single pattern can facilitate high speed, but result in loss of detail. To overcome this trade-off, we present a novel structured light technique that uses a single photon avalanche diode array, or SPAD array, to enable 3D scanning at high frame rates and low light levels. Our technique works by sensing binary images that indicate the presence or absence of photon arrivals during each exposure window. The SPAD array is used in conjunction with a high-speed DMD-based binary projector, with both devices operated at speeds as high as 20,000 Hz. The binary images that we acquire are heavily influenced by photon noise and are easily corrupted by ambient sources of light. To address this issue, we developed novel temporal sequences using error-correcting codes that are robust to photon noise and short-range effects such as projector defocus and resolution mismatch. Our lab prototype of single photon SL is capable of extreme 3D imaging and can operate in challenging SNR scenarios. We can see objects with very low albedo, such as the car tire, and the inverted view groove shown here. We can also scan dynamic and non-rigid objects, such as the rapidly waved cloth, and the fast-moving jack-in-the-box toy.
Hi, welcome to this video. We're from UCLA, and I will introduce our powerful Biolic Camera. Our camera is inspired by two later living systems, the compound eyes in flies that bring them supervision, and the time-of-flight echolocation that helps best to locate the target. The combination of them and then gives super 3D vision. The live field camera is like compound eyes with a lens state array. The challenge is no imaging speed because it needs a large format sensor to read out all the light field information. In contrast, the LiDAR camera is like time-of-flight echolocation and has fast imaging speed, but the camera format is limited to single pixel or a line sensor. So now we have the snow night field camera and a fast LiDAR camera. Then our camera combines them to achieve high-speed 3D vision. In compound eyes, for each optical unit, it only has a few photoreceptors to sense the object. Similarly, in our bio-inspired camera, instead of reading out so many pixels, we use long local acquisition so that much less pixels are needed to represent the whole object. And then we can just use the fast LiDAR camera to improve the speed. Therefore, our camera can enable unprecedented 3D vision. And here I will show you two examples. First, in this movie, our camera is doing LiDAR imaging. It's a complex scene where the letter V is rotating. Then, our camera can track through occlusion. We're moving the grid occluded by a stripe. Despite the occlusion, our camera can still see the grid pattern. Finally, for more information, welcome to our poster. We are poster number 5 in session 1. Thank you.
Smartphone cameras are becoming more sophisticated and complex with each passing year, resulting in bulky camera bumps on consumer devices. Going beyond smartphones, many applications rely on bulky, compound optics. In this work, we present metasurface optics as a replacement for bulky, compound optics. While a conventional optic relies on a series of glass lenses, a metasurface uses subwavelength nanoantenna to direct light with much finer control. In our work, we jointly design nano-optics and software processing using AI techniques, allowing us to produce neural nano-optics. To achieve this, we learn a nano-optic by using an efficient differentiable proxy function that maps phase values to spatially varying PSFs. This allows us to design the nano-optics 3,000 times faster than using full wave simulation. Neural nano-optics significantly outperforms the previous state-of-the-art and is the first meta-optics imager that achieves high-quality, wide field of view color imaging. Neural nano-optics can achieve the same quality as a conventional camera despite being over 500,000 times smaller in size. Here are side-by-side comparisons of the conventional camera and the nano camera.
Shape from texture is the ability to estimate shape and texture from an input image when neither is known beforehand. We approach this problem as a game between three players. The generator is a convolutional network that changes its weights in an effort to make patches that look the same as patches coming from the unwarper. The unwarper attempts to make patches that look like those coming from the generator by applying a field of affine warps to patches from the input image. The discriminator changes its weights in an attempt to differentiate between the two sources of patches. When the three-player game converges, the generator can make arbitrarily large samples of flat texture, and the warp field learned by the unwarper gives 3D shape. This game works for many different texture types, including ones which have required specialized processing in the past, as well as more general textures for which no prior method exists. Our three-player game works well for decomposing an image into its shape and texture, but we would also like to know when this decomposition is unique. We distill this down to the following question. Given a set of foreshortened texture patches, when can we uniquely recover the true surface normals in flat texture appearance? Each foreshortened image patch is obtained by taking a flat patch and applying to it a 2x2 warp matrix. This matrix, when multiplied by itself transposed, is symmetric, so each warp maps to a point in 3D space. We show that in general, the decomposition is unique if the points in this 3D space are not coplanar. This means that 4 patches are sufficient for uniqueness in general, but given 3 or fewer patches, the decomposition is often ambiguous. Although 4 patches are usually sufficient, we use our theory to design a new ambiguous image. All of its warps map to a plane, so there are 2 shape and texture combinations that can exactly explain the image. Come to our poster to see these 3D printed objects or hear more about our work.
Hi, my name is Renoise. I'm happy to present our work Tourbillon, an adversarial learning approach to spatially varying multi-frame blind deconvolution with applications to imaging through turbulence. Our goal is to leverage the power of generative models to tackle stochastic forward models. Prior art has already used generative models to provide prior knowledge while solving inverse problems. However, they mainly focus on settings where the forward models are known, and yet the problem gets much more challenging when we don't know the forward model. We adopt a novel approach called Adversarial Sensing. It was first introduced by Cryo-EM for cryo-EM reconstruction, which has stochastic forward models because the biomolecules being captured have random orientations. Here we show the general framework of adversarial sensing based on the example of Cryo-EM. The scene is ultimately reconstructed through adversarial training of both the generator and the discriminator. We find this framework to be a promising direction for inverse problems, and we explore extending this framework to imaging through turbulence, where the image measurements are distorted due to random phase changes in the wave propagation. Directly solving the PSF for each distorted measurement can get really expensive, and applying deep learning methods is also difficult due to limited training data. We use adversarial sensing and task the generator to produce a sharp image as the underlying signal. We then use a physics-based differentiable renderer to simulate random phase error to form fake measurements. Our training does not have ground truth sharp image labels. We can also flexibly incorporate prior knowledge to the generator, like Aydogan, if we know the underlying signals are phases. Here we show our simulated blurry measurements. As training progresses, the simulated measurements become more and more similar to the true measurements. Here we show the final reconstruction produced by the generator, which are much sharper than the observed measurements. Beyond turbulence, we have further tested it on sub-diffraction imaging. We believe these initial results have already revealed the remarkable potential of adversarial sensing. Thanks for watching.
Modeling occlusions in 3D inverse problems using mutually exclusive group sparsity. Mutually exclusive group sparsity, or MEGS, is a non-convex structured sparsity penalty that promotes mutual exclusivity between the components in the solution to an optimization problem, and it takes a simple form. The key idea today is to use MEGS to ensure that solutions to inverse problems in 3D imaging are physically plausible by ensuring that voxels that should occlude each other do so in our final solution. Consider a toy problem, where we design a structured sparsity matrix S so that first and third components in a vector should be exclusive. If we apply the penalty to a vector that does not break this rule, we incur 0 cost. But if we apply it to a vector that does, we now incur a cost. Let's consider a case study based on edge-resolved transient imaging. This is the non-line of sight reconstruction of a room using time-resolved measurements and a pulse laser focused on the floor in a doorway. If we aim to recover the position of surfaces in an angular wedge in a room using a lasso regularized reconstruction, we find that no matter how strong the regularization is, we never recover a solution similar to ground truth, and we often see components that should occlude each other in our solution. However, if we add a MEGS-based constraint with the appropriate sparsity matrix, we find we can very well reconstruct the ground truth. MEGS is well suited for modeling occlusions in 3D imaging, and typically these issues are just ignored or fixed in post-processing. We also find that MEGS ensures the solution is physically plausible during the optimization problem, which acts as a prior that improves the final solution and often results in less bias than you would have using other regularizers. The implementation of MEGS is straightforward, and there are fast algorithms that exist to solve MEGS regularized or constrained problems. Thank you.
All right, let's give a round of applause for our spotlights and also our amazing papers and invited talks and keynotes today. So just a couple of announcements. We're going to be going into our coffee break right now, and that will be followed by our poster session. So I also wanted to note that the year were just a few of the spotlights, but many of the posters that are going to be presented today and tomorrow actually have also short videos online that they also sent in, and those are online. So you can access those at the ICCP website. I don't know if I'll be, let's try to do it here. Let me try to get there. So if you go to the program, and you go down to the different, like some of these, these posters, if you click on them, they'll have videos too, so check those out as well. Other things I want to mention, so people who are either setting up their posters today or are just interested in finding one of the posters that they see on the list, if you go to the poster session, so here we're on Monday, we're in poster session 1, so here's poster layout, so you can see the, it's not always in order of where the posters are. So if you're interested in finding a specific poster or figuring out where you need to set up, you can go here. The numbers are also on the boards, but if you want a quick way to get to that, check that out. What other announcements do we have? So yeah, we're going to have coffee break right now. The coffee break, so coffee, other drinks and snacks are going to be where we had lunch today, where we sat down for lunch. So not where we had coffee break in the morning, but more where we were at lunchtime. And so that will be half an hour, so people who have posters, please set up during that time. And then in a half an hour, the poster session will start and go until 6:30 tonight. And then at 6:30, we're going to have, if you're interested in joining the Women at ICCP 2022 event, then we're going to meet at front of the auditorium at 6:30. And if you're also interested in suggestions for dinner and things tonight, remember on your badge, if you scan the QR code, you'll get to this website, and you can do, for instance, restaurant suggestions. And here are just a few. Obviously, there are many, many more restaurants, but here are just a few that are close range, along with recreational activities, if you're interested in doing any of that tonight. So anyway, thanks for making it a great first day. We'll see you at coffee hour and through the break. Did you have anything? Sorry? Oh yeah, and remember we're doing poster voting, so keep in mind the posters and demos that you really liked. You can vote and then change your mind after tomorrow, but remember that that the poster voting should be over the 2 days, not just the 1 day. So thank you all. Oh yeah. And we're going to lock this building at this time, so please take everything with you, and bathrooms that you need to use.